Monitoring. The session will be chaired by Dr. Andrew Ridley, convener of ISSMGE Technical Committee TC220, with Dr. Paul Barton, Secretary TC220, serving as a co-chair. I invite you, sirs, onto the stage. May I now invite Dr. Andrew Ridley to kindly take over the proceedings.
Thank you very much. One of the first things that we did as a TC when we were established in 2019 was to inaugurate the Dunnicliff Honour Lecture. It's something that all TCs are entitled to do. And we deliberated a little while over who to name this lecture after, but really there was only one person that you could choose for this, and that was John Dunnicliff. For those of you who maybe don't know John, I imagine there's not many in the room that didn't know him, but maybe some of the younger people here, I thought it's worth just going over a few of John's many, many achievements. The first, I guess, that everybody really knows John for is the Red Book, the textbook on geotechnical instrumentation for monitoring field performance. I think I have about 3 copies of this because I keep one in everywhere that I happen to be. It's a constant reference. It's amazing that this was written 40 years ago because there's so much relevance still in this book. And I really encourage anybody in this room who doesn't have a copy, go and get a copy because there's so much information in there. You'll learn so much. John was often asked to rewrite the Red Book, and he fervently said, no way am I going to rewrite this book. And I understand that. I wrote a PhD and I vowed never to do this sort of thing again. It's quite an undertaking to write a book. And our field changes so rapidly. And John thought there's just no way that you can keep up with this subject. But what he did was he introduced this series of invited papers he called it Geotechnical Instrumentation News, and it was published by the Canadian Geotechnical Society in collaboration with a journal. And he invited people 4 times a year to send him papers. He would edit those papers and present this as a quarterly journal almost. And there are some 90, nearly 100 or so editions of this. And they're all available on the Canadian Geotechnical Society website. And I encourage you to go and read them. Because again, I find there's so much information in there. I've actually printed out all of the copies and put them in a binder because it's like having another book. And I'm constantly referring to it. And John, being the great innovator and thinking to the future, he successfully handed this over to Pierre Choquette from the Canadian Geotechnical Society, also at RST and Orica. And Pierre is carrying this forward now with John's grace. John was involved in the Manual of Geotechnical Engineering. This is an Institution of Civil Engineers publication. And he wrote one of the chapters in this book. And again, a very, very good reference point. If any of you young engineers in the room want to know something about instrumentation, go and read this chapter because there's a lot in there. It was rewritten a few years ago with the assistance of Professor Standing, who's in the room here, and updated. But it's a great reference point. Many of you might have known John's courses. He inaugurated this course in the US many years ago. I attended several of them in the US and in the Netherlands, and also most recently in Italy. And again, John, being the great innovator and looking to the future, he successfully passed on that legacy to Paolo Mazzanti and Giorgio Pezzetti, who's in the room, and they're carrying it forward now. And every time that course is run, there's always a reference to John. Some of you may have known John for the projects that he worked on, most notably probably the Boston Central Artery, but he also worked throughout the world in Hong Kong and many other countries. But really, I think it's this series of lectures that hopefully will keep his name in the light. I think, you know, sort of one of my great thoughts when these people pass away is you've got to keep the name there. You've got to keep people knowing about who these people were. And I think inaugurating this lecture in the name of John was a great thing to do. I'm extremely pleased that John knew about this, because we inaugurated this lecture shortly before John passed away. And I was able to inform him a few months before he sadly passed away. And he was incredibly honoured and pleased. And in his inimitable style, I've taken these words from the email that he sent me when I told him, you know, sort of he was really very honoured to get this lecture named after him. And I think the words there really sum up John's sentiment. So, moving on to our second Dunnicliff Honour Lecturer. Give a formal introduction to the lecture now. Giorgio Pezzetti was born in Bergamo, Italy in 1954. He graduated from the Politecnico di Milano University in 1979 with a degree in civil engineering. In 1980, he began working at ISSMGE, the Experimental Institute for Models and Structures, also in Bergamo. ISSMGE was well known for as a research institute owned by Enel, Italy's largest power company, and was responsible for testing many of the world's large dams. His initial assignment was in the structural division, where he was in charge of laboratory and in situ tests on structural elements and performance monitoring of a variety of structures. In 1982, he joined the newly established Geotechnical Instrumentation and Investigations Division at ISSMGE, where he focused on instrumentation and monitoring technology, specifically designed for geotechnical engineering applications, large-scale tests, and long-term performance of completed structures. During this period, he was involved in a broad spectrum of relevant and challenging instrumentation projects in Italy and worldwide, perhaps most notably helping to stabilize the Leaning Tower of Pisa. In 1996, he was appointed head of Geo-Environmental Monitoring Unit at ISSMGE. He left ISSMGE to work in private industry in 2000, first as a founder of Field, a service company specializing in geotechnical and structural instrumentation and monitoring services, and since 2003 as a consultant with his own company, where he works alongside his daughter, Sylvia. Throughout his career, Giorgio has played a leading role in educating the engineers of tomorrow about the importance of high-quality instrumentation and monitoring. He has served on the ISO working group responsible for drafting international standards on geotechnical instrumentation since it was formed in 2010, and he was also a regular contributor to John Dunnicliff's courses. Together with Professor Paolo Mazzanti, he's carried this on through the world-renowned international course on structural and geotechnical monitoring. As if that isn't enough, he's been alongside me as the Vice Chair of ISSMGE TC220 since it started in 2019, and I'm extremely thankful for the support he's given to me. Ladies and gentlemen, it gives me enormous satisfaction to invite Dr. Giorgio Pezzetti to deliver the second ISSMGE Dunnicliff Honour Lecture. Giorgio.
Thank you, Dr. Ridley. May I now request Professor Dr. Marwan Al-Said to kindly welcome our Dunnicliff Honour Lecturer, Dr. Giorgio Pezzetti, with a bouquet of flowers.
Thank you very much. Thank you very much.
That's very good.
Good morning, everyone. Thank you very much, Andrew, for your introduction. Thank you to the organizing committee of this symposium for the wonderful organization of the 12th ISSMGM. Thanks to the TC220 members who selected me for this prestigious lecture. I am really honored to be here today delivering this lecture. And a special thanks to Professor Nilima, who supported me in the last month when I continuously bothered her with my request regarding my lecture. So thanks, Nilima, for your support. And finally, a special thanks to Dr. Anil Joseph, because this morning, in his introduction, he mentioned the term art, referring to the knowledge. And this helped me in confirming the idea of the title of my presentation, that is, the art of understanding. I do hope that you will realize why I am calling this the art of understanding. Well, of course, I have to start remembering John Dunnicliff. Of course, I want to remember him for his red book that has been already mentioned by Andrew. But I want to especially to remind and thanks John for what he did through the concept of the systematic approach to planning monitoring programs. It seems quite normal that as an engineering activity, we plan what we do. But unfortunately, this is not the case for monitoring, which has always or many times considered something different from engineering activity, and so not planned as it should be. So thanks, John, for this heritage that you left us. And thanks because he inspired me with the idea of keeping every detail under control. He was very active in this, and I remember that during the preparation of the courses that have been mentioned by Andrew, I sent him my slide for the presentation, and he reviewed continuously to check all small details. And this is something that I remember. And this is something which introduced the concept that looking at details, through the details, we have to remember that monitoring must answer questions. And since we are dealing with many different types of projects or structures, which one of them have different problems, we have to be very keen on small details which can make the real difference. Sometimes the difference between success or failure is due to some small details. So we have to always consider that details are something which are probably the most important part of our activity. So we have to answer questions. Why questions? Because there is something that we don't know, some unknowns. Uh, I had the permission from Alan Marr, who was the first John Dunnicliff Honour Lecturer, to use this slide that he presented in London 4 years ago regarding the problem of the unknowns. Why? Because we have different type of unknowns, or something that we don't know, or something that we have to understand. We have what is called the known knowns. That means what we know about something. The known unknowns, what we know to be unknown. We know that there is something that we don't know and we have to understand. There are unknowns, what we don't know. Something that, let me say, can happen, or something that we are not able to understand and consider. Or the missed knowns, what we know but we missed, error and omission. How many times we miss something in our activity? And the unknown knowns, what the other know but we fail to acknowledge. Defective judgment. So we have this as reference, and if we look at this from the analytical point of view, is like to have a system of equation to solve where sometimes the number of unknowns is greater than the number of equations that we have. That means that we cannot solve it. And this means that our knowledge of the world that we are dealing with is limited. We don't know everything about what is around us. So, how we solve this problem? We can solve trying to understand. Understand means to know something, to know what is happening around. And I like very much these pictures. You recognize probably Professor Peck, Ralph Peck, and his colleagues looking at something, checking, trying to see by their eyes what is going on in order to understand. So we have to understand. So we started from question to answer. We realized that our knowledge is limited, that we need for understanding. But how we can solve the problem if the analytical solution is not possible? We have to change completely our approach. And we have to use two, I don't know how to say, two capabilities that we have, the genius and ingenuity. What are they? Genius is what we can call intuition, is a person characteristics, disposition, natural inclination, or temperament, something that is inside us and enable us to understand, to know something. And ingenuity or skill is the ability to invent things or solve problems in intelligent new ways. And this probably is exactly what we have to use when we approach a problem that cannot be solved analytically. So we have to use our ingenuity and, of course, our genius. And when we are able to put together these two abilities in the best possible way, I say that we reach the level that we are doing something which can be called art of understanding. And again, thanks to Dr. Anil Joseph for using the word art. I was a little bit scared when I decided to use this term because I was not sure that it would have been something that was accepted. But now I'm sure it is the right term. So the art of understanding. The fact that I was a little bit scared is that probably when we think about art, we think about something like a nice statue, a nice painting, a melody, a music, something like that. But as the definition of art I reported here says, is a creative and imaginative human expression that uses skills we saw before and techniques to produce visual, auditory, or performative works. So it's not just a nice, a wonderful statue, but it's something more, because in order to reach that level, the author of that statue, that was Antonio Canova, has used his skill and his ability, that means his genius and ingenuity, to prepare it. This is the mock-up, the model that he did using plaster. You know, by using plaster, you can modify, you can correct something. When you prepare when you work on the marble, you cannot change what you have done. If you make some mistake, you have to throw away everything. So he prepared a mock-up, and you see all these red dots are reference points he used to measure, and he measured the position of each point to reproduce them exactly on the marble in order to be sure that the result was exactly as expected. This is something that, in my opinion, is genius. Moreover, in the past, they used, when preparing a statue, to control it. You see here these plumb lines. They've been used to control the verticality and the dimensions by measuring the distance between the plumb line and the statue. And if I put here some numbers, the level of accuracy they reached was quite high, or very, very high. This is, again, genius and ingenuity. And it was done hundreds of years ago without the instrument we have today. But there is something more. Another example. This is the Santa Maria del Fiore Church in Florence, and this is the very famous dome designed by the architect Filippo Brunelleschi, who was asked to build it when the church was already constructed to the level of the level of the starting point of the dome. And since the dimensions were so big, the diameter of the dome is 45 meters inside diameter and 54 outside diameter, was so big that it was not possible at that time to create a scaffolding inside, a wooden scaffolding inside, to support the material during the construction. So he had to invent something to avoid using scaffolding. And he made his own analysis, calculation, design, and he came out with a solution which avoided to use a scaffolding by using a new technique of self-supporting type of dome, which avoided to use internal scaffolding, but only use some scaffolding to support people during the construction. Moreover, due to the dimension of the dome and the height, you have to consider that the top of the dome is at 115 meters. He designed and built all the equipment, the machinery that have been used to rise up materials. And he designed his own instrument for controlling the construction. Is this genius, ingenuity? And the result is a piece of art. But this was roughly in the 14th, 15th century. But even if we look back, because I'm convinced that in order to advance, we have always to look back, and we have to learn from the past. If we look back, we have some very interesting example that we have to consider. For example, this is our planet, Earth. And this man, Eratosthenes, tried or wanted to define the radius of our planet. He studied a method to define it, and it was a very simple method. Probably you know it very well. So he said, in a specific day of the year, when in a place the sunshine is exactly on the zenith, the rays are perpendicular to the Earth. But if you move apart, the rays of the sun will be a little bit inclined. And you can measure this inclination by a stick and measuring the shadow produced by the inclined ray. The inclination, the angle, is exactly the angle between the two positions. By knowing the distance between the 2 points, he calculated the distance, the radius of the Earth. He calculated using the units, measuring units at that time, and by transforming those units in meters or kilometers, he obtained this value of the radius. Well, more than 2,000 years later, Irene Fisher, an Austrian-American scientist, by using satellite images and measurement, measure or define the radius of the Earth in 1960, and is the value that we are using nowadays. And she found that the radius is 6,379.16 kilometers. The difference between the two is less than 1%. So 2,000 years ago, someone has been able to define the radius, or let's say to measure the radius with an accuracy which is less than 1% less than the, let me say, the real or the actual one. Fantastic. Again, 10,000 years later, approximately in year 995, another scientist, it was a Persian scientist, Al-Biruni, made another calculation, and sorry. And by using a different technique, he calculated a radius which was 0.6% less than the actual one. Fantastic accuracy. If you consider the instrument they used at that time. And this trigger, I hope, it triggered in our mind the idea that is not the instrument itself which produces, I would say, the right solution, but is something more. Anyway, many others during the past centuries measure the radius of the Earth, obtaining different values. If we plot these values, which have been, as I said, calculated using different instruments, starting from a very simple one, Eratosthenes and others, to some very basic geodetic instrument, to satellites. If we plot this, we have this graph where the red dots are representing the radius in kilometers, and the blue dots are representing the difference in percentage referred to the actual value. We see that Eratosthenes and Al-Biruni did something very accurate. Someone made some big mistakes, probably. But what is interesting to know, or to get out from this plot, is that we can consider the first part of the measurement has been made by using basically trigonometry only, and the second part, geodesy. That means that here the accuracy was due mainly to the operator, let's say, to the man who has measured. Here, when the instrument become more and more accurate, all the results are closer to each other, because when you have good instrument, of course, it is easier to get good results. And this is something that, again, has to trigger in our mind something. That it is true that the good results are related to those who take measurement, but it is also important to have good instrument if you want to collect good results. So we have always to combine these two. And this is why, again, I think that the two properties, genius and ingenuity, must be together in order to proceed in this in our activity. Another example, this is very nice, I like this very much, is the definition of a meter. We all use meter to measure something. Probably you know the story of the meter, how it was defined. The first definition of the meter goes back to the 18th century, and exactly in 1791, and it was defined as 1/10 millionth of the distance from the equator to the North Pole through Paris. Okay, this was the definition. In order to support this definition, measurement has been done. Anyway, that was the definition at that time. The definition that we are using nowadays is this one, which is a little bit more complicated to understand, but we will see what the results. Okay, so in order to measure or to define the meter according to this definition, the Academy of France launched an expedition led by two scientists, Jean-Baptiste Delambre and Pierre-François Méchain, to measure, really measure on the ground, the distance between Dunkirk, north of France, to Barcelona. And they said, we have to measure this distance, and by knowing the latitude of the 2 points, we can calculate. We can measure the distance, we know the angle, and by knowing the angle, we can calculate the distance between North Pole and equator. Well, this expedition started to measure this and took 7 years to complete the measurement. You can imagine at that time, using instruments like this, measuring more than 1,000 kilometer distance through mountain, forest, river, cities, complete very difficult environment. They took 7 years, and the result was that the meter they calculated was 0.2 millimeter shorter than the one we are using now. 7 years of measurement, very simple instrument. Need of maintenance of the instrument during 7 years, of calibration of them during 7 years. But they succeeded, and they obtained 0.2 millimeter difference. Is this something impressive? It is due to the instrument itself? No, due to something more. So what this man and woman got is something that, in my opinion, is mainly due to their genius and ingenuity. Of course, by using the right instrument. So the point of my presentation is that, as in the title, I consider monitoring or measurement the art of understanding, as I try to explain. But what is understanding? These are two definitions I got, which are quite interesting. Understanding means knowledge about a subject, a situation, to know something. And the second one is even interesting, clear thinking. If we understand something, we have a clear view of it. So this is something. And if we want to try to elaborate it a bit, the concept, we can say that understanding is the identification of the nature, origin, and evolution of phenomenon. We are measuring phenomena. So we have to identify the nature, origin, and evolution. We have to know the limitation and unknowns. Go back to the unknowns. We have to know which are the unknowns. We have to evaluate error, live with them, and manage them. We always have to deal with error. There is nothing without error. No measurement without error. We know very well this. And we have to live with the error. We have to know them. We have to consider. We have to be able to explain why. If you are able to explain why something is happening and why is happening that way, it means that you understand the phenomenon you are dealing with. And this is something very important in our profession, we have to support decision. If we have a clear view of a phenomenon, if we know the phenomenon, if we understand the phenomenon, we are able to support those who have to take decisions. Think about the early warning system or something like that. We have to provide data, provide information to support those who have to take decisions. And that's quite important. How to do that? Andrew, in my presentation, said that I have been working at an institute in Italy called ISSMES, Istituto Sperimentale Modelli e Strutture, Models and Structure. And this is the way, at that time, we are here in the year, in the 60s or 70s. I was not there at that time. But at that time, when computers were not available, when finite element method or model were not available, they used to build physical models, trying to understand the behavior of a structure. You remember the dome of Brunelleschi in Florence and the small wooden model, the picture of the whole of the small wooden model. That was a model that Brunelleschi used to understand the behavior of the dome. Again, here, 500 years later, we built models to understand the behavior. And by instrumenting the models and applying loads to the model, they have been able to understand the behavior and to realize where are the critical points and which was the maximum applicable load, let's say, for example. And these are examples of dams, bridges, buildings, and so on. And the models, see, sometimes are quite big models. This is the model of the Vajont Dam in Italy. And the model itself is 7.5 meter height, something like that. And models were tested not only as a structure, but together with the surrounding soil or rocks, the abutment where the dam is founded, in order to analyze and understand the behavior. Here there is a short movie. Unfortunately, it is very old, from the 60s, where you see the constructional model, the measurement taken by mechanical devices, and the first electronic recording systems in order to understand the behavior of the dam, to measure the level of strain, for example. These are mechanical strain gauges that have been used at that time. And you see, the strain gauges move at an indicator which moves. And the guy here is painting the cracks that open until the failure. So by comparing the applied load to the measurement of stress, the behavior of the dam was understood. Or another example. This is the Leaning Tower of Pisa, mentioned by Andrew. Everyone probably knows it. And you know that it is leaning. Unfortunately, it was continuously leaning, and it let's say 20 years ago, or more than 20 years ago, a scientific committee was established in order to analyze the situation of the tower, and they found out that we were very close to a possible point of failure. So it was necessary to intervene and to avoid the failure of the tower. A lot of studies have been developed on the tower, on the Pisa Tower. Probably someone here in this room has worked on it. It was a very complex problem, not mainly for the structure itself, but from the point of view of the soil behavior. After studying the problem, it was decided how to intervene in order to stabilize, or better, in order to reduce a little bit the tilt of the tower and giving the tower longer lifetime. The intervention was mainly based on a temporary application of counterweight on this side in order to avoid or to limit the tilt. And the final solution was to take out material from beneath the tower, beneath the foundation, in order to induce a counter settlement which stabilized a little bit the tower. And it was calculated that a settlement of approximately 170 millimeter was necessary to reduce the tilt of 0.5 degrees. 0.5 degrees due to the height of the tower means approximately half a meter on the top. Okay, this was the idea, but of course it has to be controlled or measured some way. So this half degree or half a meter meant that the total stresses or the contact stress between the foundation and the soil have been changed, increasing on one side and decreasing on the other one. And this one was one of the most critical points to consider, because measuring the tilt is quite easy. You can use a inclinometer, you can use pendulum, you can use geodetic measurement. It's quite easy. But how can you measure the level of the contact strain stress beneath the foundation? It is not possible. So again, as you have seen for the dam, it was decided to build a model of the foundation. This is the model foundation, approximately 6 meters in diameter slab, to install some total pressure cells, build the slab and loading the slab, and then excavating in order to induce the settlement. Well, the problem was how reliable can be the measurement of the contact pressure. We all know that the contact pressure, or the pressure, is one of the most critical parameters to measure in geotechnical monitoring. And so that was a challenge. And the solution came from a long discussion that we had with the technical committee, and mainly with Professor John Barland from Imperial College, who suggested to use a special technique that is presented here very simply in this picture, using, first of all, larger diameter cells and protecting them with a thin layer of plastic, which had the scope of reducing or avoiding the problem of the possible gap between the cells and the concrete due to the change in volume of the cells during concrete curing and subsequent reduction when the temperature went down. So it was done. The model was built and tested, and the result have been used to control the deformation, the back deformation of the tower. It is something that, again, is the result of discussion and the result of the intuition of Professor John Barland, is the result of the skill of those who have worked there. Another example, this is something more different. This is a dam, big dam. Nowadays, if we want to measure the deformation of the dam or the crest, for us it's quite easy. We ask a satellite to take a picture, and from the picture from the satellite, we have all the information. And we can go back in the past by satellite. So if we take a picture today, we can compare the situation today with the situation maybe 20 years before. But at that time, we are at the beginning of the 70s, it was not possible. So someone has invented a system which is described in the Red Book. This picture is taken from the Red Book, which was called the double fluid settlement gauge, which uses a hose running on the crest in which mercury was injected, and the pressure, I'm just trying to simplify the description, the pressure exerted by the column of mercury was proportional to the settlement. We started from 0 when it was perfectly horizontal. When settlement occurred, we have a column of mercury which applies a certain pressure. And that was another interesting solution which was developed specifically for a purpose. Again, genius and ingenuity. And this is the equipment. This is the real equipment. This is the scheme, the original scheme produced at that time, and there's some measurement. Moreover, something very simple. In order again to measure in a dam the horizontal deformation. When you have a dam, which is this dam at the base is more than 1 kilometer wide. When you are dealing with that, how can you measure the movement inside the core or inside the body? How you measure the horizontal deformation? The solution which has been developed at that time was to install some reference plate with cable, steel cables, inside a hose, inside the conduit, which goes to the end of the dam, to the face of the dam, and up inside a box. And inside the box, we have counterweights. So if one point moved let's say, downstream, the specific counterweight moved down because the distance was decreasing. And so by measuring the position of the counterweight, it was possible to understand the magnitude of the deformation. Very simple solution. Sometimes simple solutions are the best one. And here we don't need to measure 1 millimeter of deformation. So another point is that we have to know which is the level of accuracy we need. But there is another man we have to thank. This is André Cohen. He is the one that has developed and patented the vibrating wire sensor, which is the sensor that we normally use and we consider to be the most reliable in the world. So he was a DEM designer, and he wanted to understand, to measure the behavior of his design, of his DEMs, the DEMs he designed. And he developed and patented this vibrating wire sensor. We are now using in many different type of instruments, which are used nowadays as normal instruments. So another man who used genius and ingenuity to solve a problem, because he had the need to understand the behavior of his design. But the title of the presentation is the art. Why art again? I repeat the definition because nowadays the art of understanding, or the art of setting up a system which enables us to understand something, is the capability of putting together such a large number of information coming from different type of instruments, which sometimes, if not correctly organized and understood, create more problem than the one they solve. So the art is to be able to understand which is the scope, how many instruments we have, which type, how to collect data, how to put together data, and how to present the data. When we are able to do that in the best possible way, we are doing something which can be called art of monitoring. An example, courtesy from NGI, from our friends we are here. Imagine a structure like this. This is an offshore platform based on foundation, which was made by a number of caissons which penetrate into the seabed in order to stabilize, in order to create the foundation of the structure. And these caissons, or skirt piles as they are called, have been heavily instrumented, as all the structure itself. And here the art was to put together all these different type of instruments, to collect all the information, to provide the owner of the structure all the information to assess the safety, the stability of the platform. And these are the results that I've been able to collect from the measurement, and again from models which have been tested before the construction, of course, in order to get the feeling, to get to understand how this skirt pile behaves. And something similar has been done onshore by building a concrete skirt pile, 10 meter high, 5 meter in diameter, which has been penetrated into the soil using a water ballast on top and measuring skin friction, horizontal pressure, skin friction, pore pressure, and so on, in order to understand the behavior of such a structure during the installation. you see here the reference instrument, just to measure the penetration of the skirt. Anyway, these were the design calculation, and these are the result from the measurement. This is the resistance to penetration. This is the base resistance. This is a skin friction outside and inside. By comparing the results obtained by instruments to the design hypothesis, it was possible to understand the behavior of the case. That's another interesting case. Last case that led me to go into a next step is this test, again from NGI, test on a reference, or on an anchoring block weighing 130 tons, which had to be installed at the bottom of a fjord. And the purpose was to measure the settlement of this anchoring block into the bottom of the fjord. And the intuition on how to solve the problem was very simple. You see here, they attached some arms to the block. To the arms, it is mounted a sort of reservoir with a hose and a pressure transducer here. When the block touches the bottom, we have a sort of head of water, or hydraulic head, from the reservoir to the transducer, and that was the zero reference point. During the settlement of this block, this hydraulic head changed, increased, and it was possible to monitor this during time. Very simple, but very useful. But the point that I want to stress with this is another one, is that the result of such a test had been presented by Helmut Biagio and his colleagues in this form, which is the famous one-page report. One-page report is something that was, let's say, introduced by Professor Peck. And he said, if you can't reduce a difficult engineering problem to just one A4 sheet of paper, you will probably never understand it. This is exactly the summary of what I'm trying to give you. That your knowledge, your understanding of the phenomenon has to be at such a level that one page is enough to describe everything. You don't need to write pages and pages and pages of report to describe something. That means that if you do that, it means that probably you have not the clear view of the situation. If you are able to summarize everything in one page, you have a clear view. You remember the clear thinking definition of understanding. So that's another important point, and introduces what I call the art of communicating. That means to be able to do all these things, but mainly to know what is worth, be able to explain why and how, why and how to do, and take responsibility. Back again to the problem of responsibility. If we are able to do that, we can take responsibility. And this is the art of presenting data. Nowadays, we have many different possibilities to present data. This is a very simple example. An embankment or a earth dam. The problem was to measure the settlement, and the solution was to use a chain of settlement plates, or what, as we call it, telltales instrument, So just some rods with transducer, which measure the settlement of each layer of construction. How to present data? You can present data in this way. This is the embankment I. The green line is the measurement, and the black line are the back analysis. This is a way to present data, but we can do better than that. For example, we can present data in this way. This is the expected or the design settlement. The green is this back analysis, and black is, in this case, different. In this case, black are the measurements. And this is something which tells us something more. Or better, immediately we can realize that we are, let's say, far away from the limit. So we immediately understand the behavior of that embankment. Well, but we can do more than that. If we plot the results in this way, we have the settlement, the embankment I. This is the expected or design settlement, and these are the measurement for the same position, a different time. Each line is a different time, and at different height. So we immediately see how they tend to go to the expected behavior. But we can do something more. We can add to this. This is a sort of cumulate settlement, but we can also have something similar to what we do with inclinometer, the local contribution to the total settlement. And here, if this line were vertical, means that the contribution of each step is constant. If it is changing, means that the material is stronger or weaker. So immediately we understand what is happening. But we can do something more. If we analyze a specific height, we can compare the stresses to the deformation, to the embankment height, and in some way calculate modulus of the material during the construction. And this helps in analyzing the result. Something more again, but using the same data. By analyzing a single point, if, in this case, we had the possibility of observing a period of no construction or no increase in embankment height, to measure, to monitor what happened during that period. And because that was a winter break of the construction, it was possible to measure, to monitor what happened during that period. This is a sort of, forgive me for this, sort of consolidation which provide us other information about the behavior of the dam. Of course, here we can also measure or monitor the pore pressure to be compared with the set. So this is something more. We started from very simple way of presenting data, and we came out with this. And this enabled the designer to optimize the parameters to be used into the back analysis and even for future activity. And what we have seen is something probably much more than just presenting data in this way. So presenting data is really a sort of art. Nowadays, we have a lot of tools that we can use for presenting data. This is something that at the beginning of my career was not possible. At the beginning, we just had tables and some plots. Nowadays, you can use the many different ways, and you can select the most appropriate. But remember this, that when you are able to use in one page, you know everything. And moreover, the best data presentation is the one that allows users to understand and to decide. Doesn't matter if it is a manual plot, or something like this. You have to know exactly what is needed, not just produce this because you have the software for this. Sometimes this is too complicated to understand, but sometimes it's useful. So we had a sort of path through the time. We started from some very simple instrument for measuring the radius of the Earth, something for measuring the meter. We had the models, we had the instrument, the electronic instrument, we have satellite. Nowadays we are using a computer and software. So what will be the future? I don't have the sphere to say what will be in the future, but I can guess. I can guess that the future will be something like this. It has already been presented before, probably by Anil. It means that in the future, fortunately, we will have the possibility to have, let's say, instrument embedded into the structure, already embedded into the structure. And the matter will be how to collect and how to use all this data. But that's probably will be the future, and something is happening even nowadays. And so the art of understanding, if we have a satellite, if we have something like the fiber optic network or the cellular phone network, I think that one of the future, or one of the main activity in the future for us as monitoring persons, monitoring people, will be how to use all these instruments which are already available, because fiber optic are available everywhere, are already installed for different purposes, but we can use them for our purpose. Cell phones, the same. Two examples. This is an example, is a project followed by the Instituto Geográfico Nacional de España, probably Giorgio know him, where the fiber optic which connect Spain to the Isles are used to measure the seismic activity of the area and to detect possible earthquakes. But the cell phones that we have in our pocket are a very powerful instrument for detecting earthquakes. Probably you know that it is something that is already existing and it's working. Someone has developed, let me say, a software which collects data from millions of cellular phone, which have an accelerometer inside, analyze all this data, and are able to detect earthquakes by measuring P and S wave reaching the cell phones. It is something which has been used, for example, or was used in Venezuela when the earthquake happened recently, and it was used and it worked. Unfortunately, nowadays, the difference in time between the moment the earthquake, the seismic waves reaches the instrument and the problems to the structure is limited to a few seconds. But who knows, maybe in the future we will be able to develop something which will improve our capability of predict what is happening. So this probably will be the future. And I report here something which I consider very interesting. Is a vision from Professor Kenichi Soga, He did this recently in Vienna at the International Society of Soil Mechanics conference, and he said something which I consider very, very important. He said, recent advances in sensing and communication are reshaping how geotechnical engineers monitor the ground and geotechnical structure. Designing, constructing, maintaining, and upgrading these systems now demands for fresh thinking to reduce material, energy, and labor. All these new technologies must be used to reduce the impact on the environment, the energy consumption, and the labor. This is another interesting scope of the future instrumentation. Achieving this goal requires a deeper understanding of performance enabled by innovative monitoring. Again, understanding. And next generation of geotechnical systems will be driven by smarter information, what we have seen, rich and continuous data from many embedded sensors to wide other satellite observations. So we will have satellite observation, fiber optic spread all over the world, but we also have contact instruments. We have a piezometer, extensometer, inclinometers. We have to be able to put together all this information in order to go forward. When coupled with advanced analytics, this data can catalyze new approaches to design, construction, operation, maintenance, and reuse of geotechnical structure. I think that this vision from Professor Soga is quite interesting, and I think we can agree with him on this for the future. So if we want to summarize a little bit the difference between today and tomorrow, today when we have to set up a system, monitoring system, we have to think about selecting instrument, installing, define installation procedure, how to communicate from the instrument to a point where data are collected. We have to think about precision, accuracy, and so on, how to work on data, how to maintain the system, and how to updating or replacing the system. In the future, if we use those systems like satellite and so on, instrument will be already available. The reliability and quality is something that we have to accept. Data will be available to anyone. The accuracy is stated by someone. We cannot say that we want to change the accuracy of a satellite because I need 1 millimeter instead of 1.1. That's it, and we have to use that. Data processing tools are almost available. We have no maintenance problems and no need for updating or replacement because someone else is thinking about that. When a satellite is old, it will be replaced by another one. We don't have to take care about it. We just receive information. It's like to have a piezometer, which is continuously changed when he goes out of order. We don't have to care about that. Someone else is. So if this will be the situation, you can say, okay, the famous chain, which is inside the Red Book, the systematic planning, will not more useful. Not at all. Because out of all the points, all the rings of the chain, what I have just presented is covering only few of them. But what is really important is, let me say, by generalize, is the design of the system and the capabilities of using data. So we have to concentrate on something different, and this will be probably the future. How we will use our resources in the future. White is today and blue is tomorrow. The design, nowadays is something which is neglected, but in the future even less, because we don't have to design probably anything if we accept exactly what someone else is giving us. Implementation, this will be a big difference. Nowadays we spend a lot of resources to implement, that means to install the instrument, to collect data. In the future we will receive data and we don't have to care about the instrument. The same for management. We don't have to manage a satellite. Data processing, something similar. Reporting, if we know how to prepare a report, will be something similar. Maintenance, something that nowadays require a lot of resources, in the future probably not. So if we save resources, where or how we use these resources? Almost finished. How to use it? First, the design. Again, this is from Kenichi Soga. I always stress this point. We need to design monitoring systems. We are engineers. We are used to design something. I don't understand why, when we deal about monitoring system, no one is considering the design. And design is not paid for. In the bill of quantity, in the contract, design is neglected. So we have to use the resources that we will have available in the future to design systems. To integrate technologies, because we have a very nice technology like satellite and so on, but before they will substitute an instrument like a piezometer or extensometer, it will take a lot of time. We have to use our resources for back analysis, because this is a very important point, because because that monitoring data which are not used to back analyze the behavior of something are useless. And sorry, disaster. The flooding now. And in the future, we will have to deal with artificial intelligence. I'm quite old, so I am a little bit skeptical about artificial intelligence. My idea is that, unfortunately, the fact that it has been called artificial intelligence is biasing our idea. Because nowadays, I think it is more a tool than a solution to something. Why this? An example. A few weeks ago, I was working on landslide data. I had a lot of data to analyze, and they started, unfortunately, the picture, the quality of the figure are not so good. I started analyzing data, starting from a lot of Excel sheets, blah, 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 and I started working on them, collecting them, and comparing with some satellite data. Well, a younger colleague told me, why don't we try to use artificial intelligence? I said, if you are able, why not? He prepared a data set. He sent this data set to, I don't know where and who, and the result in few minutes or hours was something unbelievable for me. He produces these 3D maps comparing the digital terrain model to the measurement, to the satellite images and everything. So in, let's say, seconds, he solved the problem that would have required hours or days from a single person. And this is called artificial intelligence. But is it artificial intelligence? Or is it just a very powerful tool? I leave to you the answer. I have my own answer. If we read the definition of intelligence, is the faculty of understanding, is the intellect, a mental manifestation of this faculty, a capacity to understand. The tool, the artificial intelligence, who has developed the map I have showed before, did something intelligent or intelligent have been these guys. So, well, I am at the end of presentation, and I want to leave you just a final message. I hope that what I tried to present you, thank you for solving this flooding problem without any artificial intelligence support, but human intelligence. The message, I hope that I was able to transfer you the idea that I have in mind, is that monitoring, like all other human activities, become an art when we harness our genius and ingenuity, or intuition and skill, to understand the nature of what we observe. Instruments are the means to achieve the goal, not the solution. And let me finish by this example. If we have to monitor the deflection of a bridge, we can use a very sophisticated radar or something like this. Which one is the best? Which one is the best? For sure, radar can provide us a lot of information about what is happening to that bridge. We can take out even some dynamic information about frequency of vibration, about modal deformation, and so on. This method is very simple and just provide us the value of the deflection. Maybe not as accurate as that one, but it could be enough. So again, the real problem is not which instrument we have to use, but what we have in mind as a scope and what we have in mind in terms of problem to solve. And mainly we have to understand exactly what we want to have. So that's all from my side. And let me invite you to toast with John. This is a nice picture we took probably after the first course in Italy he did. It was 2014, and we were enjoying the last night together, and he was toasting to monitoring. So I invite you to toast with John to the future, because I'm sure it will be a nice future for monitoring for our profession. So I thank you very much for your attention, and again, thanks to the organizing committee for inviting me. Thank you very much.
Thank you, Dr. Giorgio Pezzetti. I request the chair and co-chair to conclude the session.
Well, is that working okay? Thank you. Well, in the art of communication, the art of presenting an honour lecture, Giorgio, certainly deserves a story to be told, and I think you've shown that you're a master storyteller, so thank you.
Thank you.
Thank you, Giorgio, for a genuinely outstanding lecture. The art of understanding genius and ingenuity in geomonitoring from the past to the future. It was a fitting title for what you gave us. not just a technical review, but a meditation on why our field matters and how it has evolved through the work of the people who have shaped it over the years. It seems especially fitting to hear that this is the second at the second Dunnicliff Honour Lecture. John Dunnicliff spent his career insisting that instrumentation is only ever as good as the thinking behind it.
Yeah.
That data, without understanding, is just noise. And that genuine insight comes from asking the right questions before you ever install a sensor. What you've shared with us today, Giorgio, carries that same spirit forward, an appreciation of the ingenuity of those who came before us, pained with a clear eye on where our profession is heading. John built his reputation not by working alone, but by teaching, mentoring, and sharing generously with the wider geotechnical community through the courses, his writing in Geotechnical Instrumentation News, the Red Book, and simply through the time he gave to anyone who asked. I personally received that great insight from him as a young geotechnical professional. In connecting the past to the future in your lecture, you've honoured that legacy exactly as it should be honoured. Not as a fixed history, but as a living conversation that continues through people like yourself. On behalf of everyone here, thank you, Giorgio, your time, your insight, and for keeping that conversation moving forward. Thank you.
Thank you very much. Thank you. Thank you.
Thank you, Dr. Barton. I request Dr. Andrew Ridley, the chair, and Dr. Paul Barton, the co-chair of this session, to hand over a memento to Dr. Giorgio Pezzetti. Thank you, Dr. Giorgio Pezzetti, once again for a truly inspiring and thought-provoking Dunnicliff Honour Lecture. Through your reflections on the problems of the unknowns, you challenged us to look beyond what we know and what we do not know, reminding us of the